right, I'm going to do a video here where we do more domain practice, and I'm going to talk about symmetry and boundedness, which are 2 or 3 more properties of functions, okay? All right, so let's do the domain practice first. So this says find the domain of the function, so show the sign chart used in your analysis, okay? So this is the situation where I have a denominator, and the denominator can't be equal to 0. So x cubed minus 1 can't be 0. So I'm going to factor the left side by factoring out an x, and I'm left with x squared minus 1 can't be 0. But I can factor a little bit more because this is a difference of squares. So this is x times x plus 1 times x minus 1 can't be 0. So what are the zeros here? X can't be 0, -1, or 1. So I'm going to do a number line here because it's a not equals. I'm going to put -1, 0, and 1. Now x can be anything else and not be 0. So on my number line, this is going to be my domain. So it's pretty complicated, but it's not hard once you read it off the number line. So that'll be negative infinity to -1. Have to hop over -1, go from -1 to 0, union with 0 to 1, and union with 1 to infinity. Okay, because that covers all the number line. All right, not too bad. All right, now I have one here where I have f of x equals the square root of something. That's an even root. So whatever is under the square root, this 4x squared minus x has to be greater than or equal to 0. And then we're going to factor this. I'm going to factor out an x. And because that's a GCF, and I'm left with 4x minus 1 has to be greater than or equal to 0. And then the zeros here are x equals 0 and x equals 1/4. I'm going to put that on my sign chart. Now, why is this different? Because it's a greater than or equal to. That's why I have to use a sign chart, and I got to take the square root of the positive or zeros of this parabola. So I'm going to, so this is 0 and this is 1/4. Now I know I'm not to scale, but that's all right. So I'm going to put a 0 here, 0 here, and then this is an upside down parabola. So I'm going to superimpose that graph on here, remembering that I can only take the square root of what kind of numbers? Well, the positive ones. Well, the parabola has negative y values here. It has positive y values in the middle. Oops. I did it wrong, didn't I, folks? And y'all just let me do it. All right, here we go. We're going to have to see if we can resurrect our sign chart here. All right. This is me editing live action video. I heard you. Why'd you let me do it this way, right? Laughing, joking, she says. All right, here we go. We're going to start again. Here's my sign chart. We're going to have 0 here. Whoop. The 0. I don't know why I covered that up. I can still have 0. And then this is going to be 1/4. We're going to use this dark one. This is 0 and this is 1/4. And it's a 0 here and a 0 here. And I'll ask again. This is a parabola now that opens up. That's right. Mrs. Muller's a silly girl, but it's late in the evening. So here we go. Opens up because that a in front of the parabola leading coefficient here is positive, so it opens up. I'm sorry, and you can take the square root of only the zeros and the positives, which occur on the outside. Right, the y values of this parabola are positive on the outsides here. So my domain, after my mess up there, my domain is going to be negative infinity to 0 with a bracket because I can take the square root of a 0, union with 1/4 with a bracket to infinity. Right? Sorry about that. This 1/4 looks a little rough, but I hope you can see that that's 1/4. Okay? All right, let's move on and see if we can do better this next time. All right. C says x minus 2 over the 4th root of x squared plus 3x. Well, this is a 4th root, which is an even root, and it's where? It's located in the denominator. So this is going to be x squared plus 3x has to be greater than 0, and it has to be greater than 0 and not equal to 0 because it's in the denominator. All right, so let's see. I'm going to factor out an x, my GCF, and I get x plus 3 is greater than 0. The zeros here are x equals 0 and negative 3. So I'm going to do my sign chart because I have a greater than, and that's going to be negative 3. I have a 0, and 0, I have a 0. And I promise to do it right this time. This is a parabola that opens up. Here we go. And I can only take the square root of what numbers? Well, the positive ones. Can't even take the square root of 0 on the bottom, or the fourth root, I'm sorry, on the bottom because, you know, because it has a denominator. All right, so the domain for this one's going to be negative infinity to negative 3 in union with open 0 to infinity. All right. This one has two conditions. Well, what is the condition? Well, the numerator is an even root. It's a square root, so x minus 1 has to be greater than or equal to 0. And then x minus 4, because this is an and, x minus 4 can't be equal to 0. So here we go. If I say that, x can't be 4. So I'm going to put a 4 here and an open dot here because it can't be 4. And then the 0 on this is 1, so I'm going to put a 1 here with a 0. And I can take the square root of the parts of this line, y equals x minus 1, that are positive. So that has a positive slope. So I'm going to superimpose my line on this graph here. And now we're going to do my sign chart. The y values of this line, y equals x minus 1, are negative on this side, and then they're positive on this side. I'm going to hop over 4 because I can't use 4. And they're positive, the y values on this line, to the right of 1. So the domain here is going to be, now I can include 0 on this one. So it's going to be 1 to 4 with a parentheses in union with parentheses 4 to infinity. You know, and if you get stuck, I mean, you can check things out. I mean, if I put a 5 in here, right? 5 minus 1 is 4. I can take the square root of that. You see, so you can check each one of these intervals to see if it works. If I plug in negative, what happens if I plug 0 in? Because that's to the left of 1. If I plug 0 in, I get a negative 1 under here. So do you see how that doesn't work? Okay. All right, this next one. H of x equals 2x over the cube root. Now, that's not an even root anymore. That's odd. So that's not an issue, except that it's where? It's in the denominator. So the cube root of x to the fourth minus 2x squared has to be not equal to 0. Now, it's not equal to 0 because it's a cube root. So I'm going to cube both sides, and I get x to the fourth minus 2x squared. Can't be 0. I'm going to factor out my GCF, which is x squared times x squared minus 2, not equal to 0. Okay, now I have x squared times, this is a difference of squares. You can say this is x minus root 2 times x plus root 2, not equal to 0. So I'm going to do my number line, placing on there the zeros, which are what? X equals 0. Oops, I'm sorry. It's the number line because it's not equal. So this is open. And then I have negative root 2, open, and root 2, open. And I can take the square root, I can take the cube root of anything else. So the reason I don't want to take the cube root when x is these numbers is because I get a 0 in the denominator. So the domain on this one is going to be negative infinity to negative root 2 in union with negative root 2 to 0 in union with 0 to root 2 in union with root 2 to 0 because we're to infinity. I'm sorry, because we're hopping over all of these these three zeros, right? Because as this open at negative root 2, open at 0, and open at root 2. All right, and now I have k of x equals absolute value of 2x minus 7. Well, folks, Absolute value is not one of my domain dangers. So this one's domain is all real numbers. I don't really have to think about it because I don't have a denominator. I have an even root, you know? So it's not any domain gotchas. All right, now let's talk about symmetry. We're going to look at it graphically here. Okay, so we're going to look at f of x, which is equal to 2x in my first example here. So if I were to graph that, of course my line isn't perfectly straight here. Let's graph it. Not perfectly straight. I drew the same exact line. Isn't that funny? Has a slope of 2. So here it is. It's going to be pretty steep, but there's 2. Now, if you look at this graph, it's symmetric with respect to the origin. So this function is odd graphically because it's symmetric with respect to the origin. Okay? Odd origin. It's opposite. Okay? Now, this one here is the absolute value of 3x. So if I were to do that, that one is going to look like this because it's going to have a slope of 3 on both, 3 on this side and then negative 3 on this side. This one is even because it's symmetric with respect to the y-axis. Okay, now, even functions have the property, well, I'll do odd first. Odd functions have the property, when you plug in f of negative x, that's going to equal the opposite of f of x. So, for example, if I have this function here and I plugged in 1, right, I'm going to get 2. This is 2, right? So what happens if I plug in the opposite, right? Because this says the opposite of x. Well, that means if I plug in negative 1, what do I get out? Well, I get the opposite of what f of positive x is, right? Does that make sense that it would be the opposite? For even functions, when you plug in negative x to f of x, you get the same y value out. So if I were to plug in 1 here, I get 3. If I plug in the opposite of 1, which is negative 1, I get 3. So you get the same y value. That's even. So let's do some algebraic proof of symmetry. So how do you do that? You take f and you plug in negative x. So here we go. That says take, where you see x, you're going to plug negative x. So I'm going to put negative 5 times negative x plus 2. All right, and I do that math, I get 5x plus 2. Okay, is there any way that this is going to be able to be transformed to look like the original? No. So I would say f of negative x is not equal to f of x, and it's not equal to negative of f of x. So there is no, so it's neither even nor odd. Okay, now let's think about the graph of this thing, okay? If we were thinking graphically, because we have some folks that are visual folks out there. So if I have a y-intercept of 2, there it is, and a slope of negative 5, that's way up here. That's going to be a very steep negative slope. Does that look like it's symmetric with respect to the origin? Nope. And or split in half by the y-axis? Nope. So it's neither even nor odd. All right, let's try this next one. Let's say we have f of x equals x to the 4th minus 6x squared plus 5. F of negative x, when I plug that in, we're going to get negative x to the 4th minus 6 times negative x quantity squared plus 5. Now what happens when you raise a negative number to an even power? That would be negative x times negative x times negative x times negative x. So 4 negatives in a row is going to make it positive. So this is x to the 4th. Minus negative x times negative x is x squared. So that's going to be positive. So negative 6x squared plus 5 is going to stay the same. Well, look at that. What did we find? Well, we found f of x. That's the same. So I'm going to say f of negative x equals f of x, which means my function is definitely even. So we can say, therefore, f of x is even algebraically. All right, let's try this next one. To do it algebraically, we're going to put negative x in. So that's going to be the square root of negative x quantity squared minus 5. Now, do you notice when I'm plugging it in, wherever I plug it in, I use parentheses to help me out. So here we go, equals the square root of, well, negative x times negative x is, well, that's positive x squared minus 5. Well, wow, lo and behold, did we find f of x? We did. So this is f of negative x equals f of x, which implies we can say, therefore, f of x is even. Now, if I'm going to stay all capitals, I should stay all capitals, right? It's even. All right, this next one, f of x equals x squared minus absolute value of x. So let's plug in f of negative x equals, let's try, this is negative x quantity squared minus absolute value of negative x. So what happens when you square a negative number? You get a positive number. So this is x squared minus absolute value of x is, absolute value of negative x is equal to absolute value of x. And so this has implications here that says that that's f of x. So gosh, we did 3 evens in a row. So that means we have f of negative x equals f of x. Therefore, we can say f of x is even. Right? Right. Okay. So that's symmetry. Now I want to talk about a property of functions called boundedness in symmetry, okay? So now this says determine if the function is bounded above, below, or bounded from both and or not bounded. Try to do this using your knowledge of the graphs and functions from Algebra 2. If you can't figure out what the graph looks like, then you should use a calculator. All right, so what we're going to do is in our minds, f of x equals here negative 3x squared plus 3x minus 5. So what shape is this? Well, that's a quadratic. It's a parabola, and it opens, what? It opens down. So no matter what, it opens down. So that one is bounded from, it's bounded above. Just based on the fact that we know it's a parabola that opens down. Now, boundedness means there's a y value here that where it won't go above. So that's bounded from above. And the y values down low here are not bounded because you can go to negative infinity here. So that's not bounded on the bottom, but it's bounded on the top or bounded above. All right, let's talk about b. F of x equals 2x to the fourth plus 5x minus 1. Now, that's a quartic. Quartics have end behavior like this, okay, which means that no matter what's happening in the middle here, whatever, it's going to be bounded below. Now, if you don't believe it, let's look at Desmos here. And we've got y equals 2x to the fourth plus 5x minus 1. Okay, and there it is. We see that it's bounded below. All right. All right, 5 to the x plus 1. Well, that's an exponential that's shifted up by 1. Exponential shifted up by 1. So that one's bounded below. Now, you can always pause the video and graph it to make sure, but, you know, I just figured I'd talk about the ones I know about. This one is negative 2e to the x. So that means that's e to the x flipped upside down, multiplied by 2. So e to the x would be ordinarily like this, except we're making it negative, so we're taking it and we're flipping it across the x-axis. So this is going to look like this. So this one is bounded above. All right, 1 over x. That's a toolkit function that we learned about. I hope we have that memorized. That's going to look like this in the first quadrant, right? And this one in the third. That one, are the y values bounded? No, because I go to infinity here and I go to negative infinity. So this is not bounded. Sine x. Well, what do we know about sine x? Well, it oscillates between two lovely numbers, -1 and 1. So would you say that this one is bounded above and below? Yeah. So this would be just bounded because it's bounded from both. All right. Now this one, I don't expect you know what this one looks like, okay? So let's graph that one. G, which is y equals, I'm going to put a division bar, and that's going to be 10 over, oops, I have an arrow there, 1 plus, oops, I used a, 1 plus 4e, 4e raised to, I got to use parentheses, negative x. This is what they call a logistic function, which we're going to study next semester. Okay, but if you look at the picture, it's got a horizontal asymptote here and a horizontal asymptote at 10 and kind of does this. So this one is, would you say, bounded? Yeah, it's bounded. And when you say bounded, you mean above and below, because the y values aren't going to infinity in any situation there, okay? All right, this one is the square root of 4 minus x squared. Now, I wouldn't expect that you know what that looks like, but we're taking the square root of a parabola. It opens down, right? Now, what numbers can you take the square root of? This one, and you can take the square root of these. So I think it's going to look something like that, and I'll graph it for you in a minute. But that one is bounded below. But let's prove it. Y equals the square root of 4 minus x to the second. Do you see? It's bounded below. I knew you believed me. All right, let's look at the next one. This is the absolute value of x minus 2 plus 3. Well, this is the absolute value function shifted to the right by 2 and up 3. 1, 2, 1, 2, 3. And then opens up, right? So this is bounded below because these arrows go on forever. So this is bounded below. Oh, a lot of bounded belows. X to the 7th. All right, well, it's got a 0 at 0. And this is an odd root. So odd end behavior, so it's going to look like this. Okay, is that one bounded? No. It's like x cubed or x to the 5th or x to the 9th, right? It's not bounded. All right, this one is the square root of x plus 4. Well, that's shifted, the square root function shifted to the left to -4 and goes like this. This one is bounded below. And then I have got the cube root of x. Well, the cube root of x is one of our toolkit functions, and it looks like this. And this one is not bounded. Okay? All right, symmetry. Some more practice with symmetry. So this means that if we have an even function, let's recall what that means. That means if I plug in a negative x into f of x, I should get out the original. If you're odd, if you plug in a negative x, you should get the opposite of the original. Okay, all right, so let's try some work here. Okay, so here we go. I'm going to rewrite this as, this is the cube root of x squared, right? Because the roots are closer to the bottom. So that's the cube root of x squared. So we're going to plug in f of negative x here equals the cube root of negative x quantity squared. Well, what happens when you square a negative number? That's going to be negative x times negative x, which is x squared. So this is equal to the cube root of x squared. But guess what? That's equal to f of x. So what can we say about f of x? We can say, therefore, f of x is even, because it fits this mold. All right, what about this one? This is the fifth root. So f of x equals the fifth root of negative x minus negative x cubed. All right, so we get the fifth root of negative x. Now, when I cube a negative number, that's negative x times negative x times negative x, is going to be a negative number. So negative times a negative is positive, so this is positive x cubed. Now it's close to this, but it's not quite. So I'm going to say fifth root of, I'm going to factor out a negative, and I'm left with x minus x cubed. And can we take the fifth root of negative 1? The answer is yes. So we can pull out a negative 1 and say this is the fifth root of x minus x cubed. Well, we've arrived back at f of x, so this is f of negative x is equal to negative f of x. So that, what can we say about our function? Therefore, f of x is odd. All right, let's try this one. F of negative x is equal to negative x quantity squared minus 4 over negative x. So when I square a negative, I get x squared minus 4 over negative x. And I can pull the negative out in front mathematically and say that this is x squared minus 4 over x, which is equal to what? The original. So this is equal to negative f of x. Therefore, we can say f of negative x is equal to negative f of x, and f of x is odd. All right, let's try D. F of negative x equals negative x quantity cubed over 4 minus negative x quantity squared. And when you cube a negative number, we get negative x times negative x times negative x, which gives you negative x cubed over 4 minus x squared. And this looks like negative x cubed over 4 minus x squared, which looks an awful lot like f of x. So that equals f of x. And we can say f of negative x is equal to f of x, which means, that's right, f of x is even. So I found the original. All right. This next one, I'm going to plug in negative x. F of negative x, maybe I'll put a negative x here, equals negative x minus negative x quantity cubed over negative x. So let's see what happens. A negative x on top. Remember, negative of negative x cubed, that's going to be positive x cubed over negative x. And this is not what the original looks like, so I'm going to do a little bit more work. I'm going to factor out a negative in the top, and I get x minus x cubed over negative x. And so the negative over the negative is equal to a positive. So I get negative, so we're going to get, so these negatives are going to become a positive. So we're going to get x minus x cubed over x, which is equal to f of x. So f of negative x is equal to f of x, which means we can say, therefore, f of x is even. All right, next one. F of negative x equals negative x times the square root of negative x quantity squared plus 3 equals negative x times the square root of, well, when I square a negative, I get a positive. So this is x squared plus 3. And lo and behold, that looks like f of x. So this is negative f of x. And so I can say f of negative x is equal to negative f of x. Therefore, f of x is, f of x is odd. All right, let's try this one. F of negative x equals negative x quantity cubed over negative x plus 5 equals negative x to the third over negative x plus 5. Now, even if I were to factor a negative out of the denominator, I will never get back to one of them them both being the same sign. So I'm going to say f of negative x is not equal to f of x, and it's not equal to negative f of x. Therefore, f of x is neither even nor odd. So I couldn't get back to the original. All right, last but not least, f of negative x equals the square root of negative x. Well, I can't take the square root of a negative number, so the negative has to stay in here. And guess what? If you think about the square root of x, this function here, does that have any even or odd symmetry? The answer is no. So f of negative x here is not equal to f of x, nor is it equal to negative f of x. Therefore, f of x is neither even nor odd. So, in summary, boundedness talks about the y values, okay? If your y values are going to positive or negative infinity, like they do on this x to the 7th, your function is not bounded above or below. It's just not bounded because the y's keep getting bigger and bigger, okay? This one is bounded above because there's a y value for which it does not go above. This one is bounded below because there's a y value for which it does not go below. Sine is bounded from above and below because there are y values that it doesn't go above and below. All right, and symmetry. This is even symmetry if you are symmetric with respect to the y-axis. And algebraically, what do you do to prove it? You plug in negative x and see if you can find the original function or the opposite of the original function. And if you can't find either, it's neither even nor odd. Okay, so I wanted to do a quick video on domain and symmetry and boundedness. All right, you guys have a great rest of your day. Thanks for listening.